Skill 5, solving polynomial functions using factoring. Okay, in order for us to solve a polynomial equation, it has to be equal to 0. Again, and I know I've said this before, but it's so important. We set it equal to 0 because when we solve, we're solving for the x-intercepts. X-intercepts are solutions, your roots, your zeros. So if I'm an x-intercept, my y-coordinate is 0. So that is why we do that. All right, that means I have 3x to the 4th minus 12x to the 3rd, and I need to add 21x squared to the other side so that I can see how in the heck I'm going to solve this. Well, number one rule of factoring is to always look for the greatest common factor. Is there one? Well, yeah, 3x squared is our greatest common factor, so I'm going to factor that out. That leaves us with x squared minus 4x plus 7 equal to 0. All right. So then, zero product property says that we can take both of these factors and set them equal to 0 and solve. Yay. Okay, well, for the first one, we get x squared is equal to 0 when we divide both sides by 3. And then we get x is equal to 0. That's one of our solutions. For the quadratic, we can factor, we can complete the square, or we can use the quadratic formula. It doesn't factor, unfortunately, because 7 and 1 are the only factors of 7, and they don't add to 4. So what I'm going to do is I'm going to complete the square just for practice, which means that I have x squared minus 4x plus some number equal to negative 7 plus that same number. Well, half of negative 4, which is the coefficient of my linear term, is negative 2. If I square that, I get 4, and that's what we're adding to both sides. Okay, so then we can factor this perfect square trinomial to be x minus 2 squared, because that is half the middle term, equal to negative 3. Well, if I'm going to keep solving, we get x minus 2 is equal to plus and minus the square root of negative 3. Let's keep solving for the imaginary. Doesn't say to solve under the real number system, so that's okay that we're doing it. X is equal to 2 plus and minus I rad 3. So our answers are 0 and 2 plus and minus I rad 3. Since there are 3 solutions, but only 2 of them are imaginary and only 1 of them is real, this means that this function is going to intersect the x-axis only once. Good, very good. Okay, well shoot, we know we can factor out a GCF. We know we can factor a trinomial, but what about this new one? We are going to introduce a new factoring pattern called the sum and difference of cubes. And it looks like this. If I have a cube plus a cube, or if I have a cube minus a cube. What the heck? How do I factor? Ladies and gentlemen, there is a beautiful pattern, and it goes like this. And just do me a favor, put your pens and pencils down for a second so you can watch and listen and absorb everything that I'm about to say, okay? So if it is the sum of cubes, it is a plus b, a squared minus the product of ab plus b squared. Again, keep those pens and pencils down, please. For the difference of cubes, it factors to a minus b, a squared plus ab plus b squared. Pens and pencils down. I know it's driving you nuts, huh? Okay, there are things to notice about the pattern. First off, a, b, a squared, the product of ab, b squared. The pattern in which the letters are written, the which they are multiplied and squared, is the same regardless of whether it's the sum or difference of cubes. A, b, a squared, a, b squared. If you can remember that, you're halfway there. The other cool thing about this pattern, and this is super cool, is that it uses soap. You know, like when you wash your hands and we're supposed to use soap, especially now that we've got COVID and we have to be extra, extra clean and careful, right? Soap. How do I spell it? S-O-A-P. Huh? It's the same sign. It's the opposite sign. It is always positive. Same sign. Opposite sign. Always positive. So if you can remember those two simple things, boom, you've got this pattern down. This is the sum and difference of cubes new factoring pattern. And I know a lot of times we think, wait a minute, why can't it just be a minus b times a minus b times a minus b? Well, do me a favor. When you have a second, multiply that out. Nothing cancels. You end up with a polynomial that I believe has 6 terms? Maybe 5, I forget. But it isn't our sum and difference of cubes. Perfect cubes. All right, so let's do an example with one. That way we can get a little bit more comfortable with this pattern. And notice right away, if I'm going to solve, I have to set it equal to 0. So 2x cubed plus 54 is equal to 0. Well, I notice that it has an x cubed and then a constant, but neither one of them are cubes. Oh, that's right. Patterson said to always, always look for that greatest common factor. And they have one. So let's divide everything by 2 and see where that leads us. Well, we get x cubed plus 27 as equal to 0. Beautiful. This is the a cubed. This is the b cubed. Okay, so we're dealing with the sum of cubes, which means we're dealing with the first pattern. We need to figure out what a is and what b is in order to plug it into the pattern appropriately. How do we do that? Well, a is the cube root of whatever a cubed is. B is the cube root of whatever b cubed is. So for the purpose of example 9, a is the cube root of x cubed, thus it is just x. B is the cube root of 27, which means it is just 3. In order to find the values that you substitute into the patterns, be it sum or difference of cubes, take the cube root of the first term, that's your a value. Take the cube root of the second term, and that is your b value. So here we go. I remember that it had a binomial and a trinomial. Okay, it was a, and then b, which is 3, okay, and then a squared, so x squared, a times b, so 3x, and then b squared, so 3 squared is 9. Whew, okay, a squared, b squared. We did a good job there. Okay, we then need to remember to soap. So same, it's the sum of cubes, so same, opposite, and always positive. Sweet! Now we can set each of these factors equal to 0 and solve. So x plus 3 is equal to 0. X squared minus 3x plus 9 is equal to 0. On the left-hand side, easy peasy lemon squeezy, x is equal to negative 3. On the right-hand side, let me save you some time and effort. When you use the sum or difference of cubes factoring pattern, the trinomial that results from this pattern will never factor. Ever, 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 ever. So you might want to write that down. The trinomial that results from this factoring pattern will not factor. We will always have to either use completing the square or the quadratic formula. Here we go. We use completing the square already, so I would like to use the quadratic formula. X is equal to negative b plus and minus the square root of b squared minus 4 times a times c, all over 2 times a. Okay, keep going. So in the numerator, we get 3 plus and minus the square root of 9 minus 36 all over 2. If we continue to simplify, we get 3 plus and minus the square root of negative 27. But don't be afraid of the negative because, yes, that's right. We can simplify this now. All right, here we go. Horizontally. 3 plus and minus, I'm going to pull out the imaginary, which is the square root of 1, right? And then 27 can reduce to 9 times 3. So the square root of 9 is 3. 3i rad 3 all over 2. And that's as far as we can go. So when, as a refresher, we use the sum or difference of cubes factoring pattern, first, we identify what the cube root of the first term is because that will be our a value. And then we identify the cube root of the second term. That is our b value. Sometimes we'll need to factor out a GCF. When we put it into the pattern, our a and our b value, the trinomial will never factor. So you'll either have to use completing the square or quadratic formula. Dun, dun, dun. That was it. Good luck, guys.